let us continue talking about special relativity, right? So in the yeah, I kind of want to use this video because it has the really good animations that I can. Wait, let me find the place. Okay, so I'm gonna use this animation to help us imagine things easier, because the good thing about internet nowadays, right, is that people have been making really good animation, and it helps us a lot in understanding more complicated subject. So there's this channel called Crash Course that covers a lot of basic topics in physics. So not just in special relativity, but if you browse the channel before, you can see things like Newtonian Mechanics, actually everything that you have been learning this here, thermodynamics and all those things. So and the limitation as we teach in this class, right, is that I can only write things here. Even if I do animation, as you can see, right, it's like very basic and very unprofessional. So those people who are doing it online have all the professional animation that make everything looks nice and easy to understand. So yeah, so if you can access it, you can go ahead and take a look. For those who China who can get into YouTube, right, yeah, if you want any particular if you want the special relativity video, I can give you the illegal one on the OneDrive. Okay, so in any case, let us continue with the concept of Lorentz transformation. Right now, last week we have been discussing how we have two frames, right, and we call them Alice and Bob. So usually Alice is having a frame S and Bob is having a frame S prime, and these two are moving relative to each other, and we are talking about inertial frames. Okay, so inertial frames, and the reason why we talk about inertial frame is that is where special relativity is valid. If one of them is accelerating or both are accelerating, then our calculation do not apply anymore. We actually need to use general relativity, which is much more difficult and more advanced. So let me remind you, we have two postulates of special relativity. It's about the laws of physics, right? And then the second postulate is the speed of light. So speed of light is always constant for any frame, which is 10 to the power 8 meters per second. Okay, so that is the basic postulate of special relativity, and so in our later discussion, right, we will always talk about postulate 2 only. And before we continue further, right, let me comment a little bit about why there is a postulate 1. So it seems like it's not important, but actually it is important, and the key point is the inertial frames. So the concept of relativity is that, if you're inside an inertial frame, right, and then if you see something moving relative to you, right, and the idea of special relativity is you cannot really say whether you are moving or actually you are not moving, but the other frame is moving. So in the animation, in the video, in example, right, let's say you are in a train, and if you ride the train, you actually experienced this before, right? If you are sitting on the train, right, and then you're waiting for the train to start but haven't started yet, so you're waiting a very long time, right? So the train is stopping the whole time, and then you look out the window, and suddenly outside the window you see something moving, and then you thought, oh, finally we are moving already, and then actually you are disappointed. Actually it's not you moving, but the train next to you that is actually moving, right? So at that short instant, you weren't sure which one of you are moving relative to the ground, right? Whether it's the next train or yourself. And yeah, so that is, sometimes you cannot distinguish, and usually you cannot distinguish is when you are inside an inertial frame. Okay, so the postulate 1 says that the laws of physics are the same in every inertial frame. Why do we say laws of physics same in inertial frame? So if you are in an inertial frame, right, let's say a train or a bus, if the bus is traveling at constant speed, you can sit down on the bus, you can eat your dinner or write things, everything behave normally on the bus, right, as long as the bus is traveling at constant speed. So if you drink water, everything is okay, right? So the laws of physics behave the same way as you are inside your house, right? But if the bus is accelerating or decelerating, so let's say the bus suddenly break. If the bus suddenly break, right, when you're drinking water, suddenly you spill your drink. Why? Because the laws of physics for that moment change differently. There's an acceleration into the system, so your actions do not match what you want to happen, and that's why people fall down if the bus is braking too hard, or yeah, things go a bit out of control, right? That is when your frame is not inertial. So when the frame is not inertial, there's an extra acceleration, and that is why the system is no longer symmetrical. It's not the same. So if everything is constant velocity, then there is no extra force, so our actions all behave consistently with our expectation, right? So hopefully everyone is clear with postulate 1. Let us proceed on with to discuss the consequences of postulate 2. And postulate 1 is implicit here because we are using the same equations, all these things. So this is the section 10.3, Lorentz transformation. So in the last class, I have been convincing you that the speed of light is the same in all frames, no matter how they are traveling to each other, right? So that is the concept that everyone was like struggling to understand, right? Because this is very new and unusual. This is not what we experience every day, and we will try to understand the consequences by seeing how it works. Okay, so in order to make sure speed of light is the same in all frames, the only way to make it same is that time and distances are different, because speed is distance over time. So the consequence of these two postulates is that time will change for a relative frame, and also distances will also change, right? So like Kai Heng said, if he's running very fast, late for class, is because his time changes. So we want to calculate exactly how much the time change depending on the relative velocity. So this is where we talk about time dilation. Okay, so time dilation. Dilation means in English something expanding. So the consequence is we are calculating a phenomena where time is slower compared to other frames. So let us consider this scenario, right? So we will consider a thought experiment, the Gedanken experiment, where I have Alice on the ground, and then she is using frame S. Oh yeah, by the way, I forgot to talk about this also, right? So in our subsequent discussions, we will mention a lot about event. So what is an event? This one is also easy to understand, right? Let's say you want to attend an event, your graduation ceremony or a wedding. To attend the event correctly, you need to know what time, and you need to know the venue, right? What time it starts, so you go to the place at the correct time, and you go to the correct room. So that is an event. That means event is something that requires a time and a position. So if time and position, so if I am Alice and I want to make sure, I want to observe a certain event happening, then I need to record the time and I need to record the position. So position is three-dimensional vector, right? R3. So right now we include time as an additional piece of information, and this is why in special relativity we consider space-time as a 4-dimensional vector space, right? So this is your linear algebra vector space dimension coming in, right? 4 dimensions. Okay, so so if event measured by Alice will measure a certain time and a certain position, but Bob is moving relative to Alice, so his coordinate system is different from Alice. So Bob's coordinate system will be some other number, t prime, x prime, y prime, z prime. Okay, so Alice and Bob will measure different coordinates, and right now we want to see how these two are related to each other. Okay, so so now we go to time dilation. He actually ran more than 100 in... Yes, so that is the length contraction thing also, which is something we'll discuss also later, right? So yes, correct. So Alice is on the ground. We have using the frame S, and then in this scenario, Bob is on the train. and Bob is using frame S prime and moving at speed u relative to Alice. So okay, so Alice and Bob are moving relative to each other at a speed u. Okay, so right now what we want to consider is I will just use this animation to help me explain. So what we are doing is I have a laser that is shooting across the train, and then there's a mirror. So a laser will be emitted from Bob, and then it will be reflected by the mirror and come back to the laser source again. Okay, so let's see what's happening here. So according to Bob's perspective, you see this. Okay, so this is what we want to calculate now. What's TV? Time, length. TV. Oh, movie. Yeah. So movie is a three-dimensional object because you have different time, right? And at different time you got a different XY plane. So every different slides, right? So different frames. So time, length, correct. So it's a three-dimensional vector space. Okay, so yeah. So as what we are doing now, right, is I have a train, right? So I have a train, and then Bob and Alice measure the same phenomena. What is that phenomena? So I have a laser. I will shine the light of the laser, and then the laser will get reflected back. Okay, so so we will calculate this phenomena, and we will conclude that the time measured by Alice and Bob turns out to be different. So let us start by considering measurements by Alice. Okay, so what does Alice measure? Okay, so so let me draw the scenario that was in the animation is definitely much better, but let's say I have a train here, right, and then Bob is here. So let's say the origin, our main assumption usually to make it easy is, Alice and Bob are having the same x coordinate at the same time, and then I have a laser here, and then I have a mirror here. Okay, so the laser will shoot at the mirror. Okay, so the laser will shoot at the mirror, but Alice is standing outside. So what does she see? Right, she will see the train moving in front of her. So after a while, the train will move. Right, so the train will move. So let's say the train was originally here. Then so the train will move. So let me try to draw this properly. Okay, so the train will move. Right, so the initial position was here, and then from the perspective of Alice, right, the light, definitely the light will shine towards the mirror and get reflected back. But if you're outside the train, then you see the train moving in front of you. So originally the light started from here, started from the laser, and then it shine towards the mirror, and then it will come back on the train, right? So it will come back on the train. So the light will travel in this direction, right? So the light will travel in this direction, and then the distance traveled by the light, if you look at this is two triangles. So this is L over 2, this is L over 2. And we consider the height of the train to be h, right? So this is h, okay? So this is, and then from here to here, right, there's certain time interval later. So this is time 0. So this is time equals to 0, and this is time equals to some time interval later, so delta t, right? So this is a time interval of delta t later. Okay, so during this time, delta t, train, well, we can consider the distance traveled by the train. So the train has traveled a horizontal distance of L, which we can calculate because the speed of train relative to Alice is this one, right? Is u. So the speed is u. So L is u times the time interval. So this one, everything here is measured using Alice coordinate system. Okay, so L is u delta t. And then how do I calculate the, so I can calculate, so this is the formula for L, right? But I want to calculate the speed of light. So the speed of light is the distance traveled over time. Okay, so yeah, so this is the time. What is the distance traveled by the light according to Alice? Okay, so distance traveled by light measured by Alice is, I'm going to call this distance to be delta distance, so measured by Alice, so I'm going to put A here. And then what is this? This is just a triangle, right? So this is, the height is h. So this diagonal line, I can use Pythagoras theorem, right? So this square plus this square, square root, I get this diagonal line, and this is another diagonal line, so it's twice. So it's 2 times h square plus L over 2 square, and then square root. And we have also calculated the L, right? So L is u delta t. So I'm going to put this L into here, so that the distance traveled by the light is h square, and then plus L is u delta t over 2. The whole thing is squared, and then we take the square root. Okay, so this is the distance traveled by the light, and given this distance, and I know the time interval, so what is the speed of light measured by Alice? So speed of light measured by Alice is CA, but of course measured by, it should be the same for everyone, but let me say CA first. So speed of light is the distance over time, right? So distance over time is this thing divided by delta t, so it's just 2 over delta t, and then h square plus u dt over 2 square, and then take the square root. Okay, so I got my first result. This is the speed of light measured by Alice. Okay, so using this laser, we can measure the speed of light. Now, we can also see what Bob measures. Okay, so measurements by Bob. So let's consider, what does Bob measure? Okay, so Bob is very simple because Bob is on the train together with the laser. So he is inside the train. He is inside the train together with the laser and the mirror, and laser and mirror is not moving relative to Bob. So if the laser and mirror not relative to Bob, then the laser will just travel straight up and then come back down, right? So this is the laser distance traveled by the laser. Okay, and between the time going up and coming going down, right, the time interval for Bob, we let time interval measured by Bob is equals to delta t0. Okay, what is the time interval for both cases, right? The time is the time where the laser starts and come back to the laser again, right? So that is the time interval. So time interval for Alice is time the laser start and come back to the starting point. Same thing for Bob, the time the laser start and then come back down, this is the delta t. So this one is the time interval. Then the distance traveled is very simple, it's 2h, right? So distance traveled by light measured by Bob is what? So distance traveled by light measured by Bob is delta L measured by Bob is just 2h. So speed of light measured by Bob Bob is c Bob, right? And of course is distance for Bob over time of Bob. The distance is just 2h, right? So 2h is equals to delta t0. So therefore I conclude that I have an expression which I will use to substitute later. So h is equals to cb delta t naught over 2. So this is equation 2. So I got these two equations now, right? So this equation contains speed of light measured by Alice, speed of light measured by Bob. So next we will use postulate 2. This 2 is actually the same value. Okay, so we will do this next. Okay, so does anyone have any questions so far? Yes, anime is 3D. That's kind of true lah. Yeah. Have you guys heard about the 4D cinema? 4D cinema. Well, no, because speed of light. So speed of light is the same no matter how you measure. So if you're talking about light, there's no delay. Time is, yeah. Okay, so that's the other issue here. Correct. So the water splashing is the fourth dimension, they say, right? Is the fourth source of information that convey to you on the cinema. Yeah, they splash water on your face, and then the chair will shake around, and then they blow air onto you also, right? So right now I have two equations, right? I'm going to substitute equation 2 into 1. So 2 is an expression for h, right? So I'm going to substitute this h inside here. So I'm going to substitute 2 into 1. Okay, so that my equation 1 now becomes speed of light measured by Alice is 2 over delta t, and then the expression for h is cb delta t over 2 square plus u delta t over 2, the whole thing square also, and then I take this out, right? I got this now, and then now I use postulate 2, right? Because yeah, so let's use postulate 2 now. Let's not delay. Postulate 2. According to postulate 2, speed of light measured by Alice should be the speed of light measured by Bob. So I'm just going to call everything c. Right? So everything here, all the speed of light should be just c. So c is just 2 over delta t. And then c dt 0 over 2 square. And then this is u delta t over 2 square. And then take the square root. So everything is c now. And I want to find a relation between delta t and delta t naught. So this is time interval of Bob, this is time interval of Alice, and time interval of Alice appear in two places. So let me just simplify this equation. So I'm going to square both sides. So squaring both sides, I got this over 2 delta t square, and then this one is opening the square and simplifying. I got c delta t over 4 plus u square delta t square over 4. Right, so I can cancel the 4, and I got c square dt square is equal to c square dt naught square plus u square dt square. So this term, actually I can put them together. So c square minus u square delta t square is equals to c square delta t0 square. So my time interval according to Alice can now be related to the time interval measured by Bob. So now I take the square root of both sides, right? So I got wait, I'll square root later, right? So I'll do this here, c squared minus u squared. Okay, so this usually we simplify this out, so we got c squared delta t0 square. I factorize the c out so I can cancel the one upstairs. So I can cancel this, right? And now I take the square root of both sides. So if I take the square root of both sides, I got dt0, and then I got the downstairs factor 1 minus u squared over c squared. So now we have the, so this one I talked about like just telling a story last week. Time works differently for different frames. Now we got a precise calculation. Time measured by Alice is here, time measured by Bob is here. They are not equal to each other. There's an additional factor. So we call this the Lorentz factor. So we're going to call this term gamma which is 1 over use over this thing. Okay, so this is the Lorentz factor. Okay, so this is the Lorentz factor, and of course, right, we will prove this later. Nothing can travel faster than the speed of light, but our u generally was always going to be smaller than c. So 1 minus a number smaller, it will make this smaller. Square root will be even smaller. So the factor is always gamma larger than 1, right? So the gamma is always greater or equal to 1 for the range of 0 to u to c. Okay, so this Lorentz factor is gamma, and this factor is always greater than 1. Okay, so that means time for Alice is longer compared to the time measured by Bob. Okay, so what is the time? The time measurement here is that the time it takes for the laser to come out and come back again. So according to Alice, it takes a longer time for the laser to come out and come back. For Bob, it takes a shorter time. So the same event, right? The same event is actually taking a shorter time for Bob compared to Alice. Okay, so that is what is happening over here, right? So since I call this Lorentz factor gamma, so this whole thing is just gamma, so we are just going to call this formula delta t is equal to gamma delta t0, where gamma is just 1 over u squared over c squared. Okay, so this is our time dilation formula. Okay, so yeah, so this is our time dilation. Okay, so does anyone have any question? Yeah, so if you go to a 4D cinema, better go to a better quality one to make sure you don't get the dirty water. So does anyone have any question? So are the concepts, is this too strange, or actually everything makes sense now? Okay, so yeah, so time dilation, but there's actually an important question, right? When you have two frames, right? When you have two frames, the question is, here's my question. Okay, it looks like it makes sense now, but here's the question, right? Right, so let's say Alice and Bob both measure time interval. Okay, so both measure a time interval, so they get a result by Alice and then a result by Bob. Okay, so yeah, and then they're moving relative to each other, of course, right? So but of course actually we know the answer, right? So this is Alice and this is Bob. Okay, so let me change the question a bit. So yeah, so let's take another name, Eve, and what's the fourth common name? I don't know. Yeah, Albert for Einstein. No, let's say yeah, Carl. Okay, so both measure a time interval. I avoid using Alice and Bob because we know the answer for Alice and Bob, right? So let's say I have another two person, so measure a time interval. Okay, so let's say delta t for Eve and delta t for Carl. Okay, so I have two measurements. Then how do I which one do I use? Okay, so my result delta E is equals to gamma Carl or delta T Carl is gamma delta T if. Okay, so how do you know which one to use? Okay, so how do you know which one gets the longer time and how do you know which one gets the shorter time? Right, so this is the common question that confuses students, that we know the dilation formula, right? It's very easy to remember and memorize, but the mistake will happen if you use the wrong direction, right? If you use the wrong way, right? So can you, yeah. How light becomes a triangle when Alice sees it? Well, let's show this again. So Bob is in the train, so he will become this. This blocking the view. Yeah, so that is how you get the triangle. Okay, so yeah, so which one to use, right? So the answer is we need to understand the concept of the proper time. Okay, so let me write down the page number. So the answer is proper time. Okay. Okay, so proper time is an interval, is a time interval between events measured in a frame where it has the same position. Okay, so yeah, so the proper time is the time interval between events measured in a frame that has the same position. Does that make sense? So let me explain why. So in the train example, right, in the train thought experiment, what is the event? So in the train, the two events are, okay, so the first event is laser emitted and then laser returning from source, and then laser returning to the source. Right, so my source, that's laser pointer, right? Basically laser pointer. So the time where the laser goes, and then until the time the laser come back. So what is the time interval? So the time interval between these two events is some delta t or delta t0, right? The time interval is different, measured by different persons. Okay, so in Bob's frame, right, events 1 and 2 occurs in the same position. Position or same coordinate x prime, right? So what does Bob sees, right? So according to the Bob coordinate system, right, if he uses a coordinate system x prime, right, the laser leaving and coming back will be in a different position, right? So, but for Alice, right, for Alice, if Alice uses, according to Alice, what she sees is if she uses a coordinate system, right, the laser coming out is in a different position than the laser coming back. So in Alice frame, events 1 and 2 events 1 and 2 occur in different positions. Okay, so that means for same position for Bob, different position for Alice. So therefore, our conclusion is proper time belongs to Bob. Okay, so Bob measures the proper time, right? So Bob measures delta t0, and therefore Alice measures non-proper time. So non-proper time is going to be the dilated one. Okay, so the non-proper time is dilated relative to the proper time. Okay, so that's why we got this formula. So gamma t0. So this part is always, you need to identify who gets the proper time. Okay, so that is the tricky concept, and because proper time is we say it's the original time, but it's also not correct to say, but it's a time where the interval happens in the same place. So that's, and then the dilated one is where the things are not happening in the same place. So this is why if we see other people moving, right, it is, you see the clock in the other frame that is going to run slower, because the clock is moving relative to your coordinate system. So every time the clock goes 1 minute, it is going to be at a different place all the time. So when you see the time in other people's frame, you're going to be slower. So you see your own frame to go at normal speed, but frames moving relative to you will be running slower compared to you. Okay, so yeah, do you understand? Or does that make sense? Oh yeah, so you're answering Charles' question, right? Yeah. Yeah, so the reason is this whole calculation, right? This whole calculation, because the speed of light is the same. So yeah, so this whole thing, that is what we are trying to conclude. So after all this calculation, we conclude that the frame in other people will run slower compared to you, because the laser, if we see the laser moving like this, right, the laser leaving and coming back is happening at different positions. So after we done this calculation, we conclude that the time measured by Alice is gamma times time measured by Bob. Gamma is always larger than 1. So from here we conclude that if you see a laser in other frame, it will take a longer time compared to if you are Bob, you are together with the laser. If you are together with the laser, you will measure the proper time. Okay, so that is the thing. Yes, so the external one is the twin paradox, which is what I'm going to talk about next. The twin paradox. Actually, before we go to twin paradox, let us do some simple example, right? Yeah, so do some more concrete calculations first, and then we talk about the twin paradox. The twin paradox, the solution is, I feel, is like very, the paradox sounds intriguing, but the answer is actually very boring. So yeah, it's not that interesting to talk about. Okay, oh yeah, let me bring up I haven't opened up my notes yet. Okay, so let's do some examples, time dilation examples. Yeah, so this is the part that I rewritten. So if you downloaded before last week, it's not yet updated. Where's the example? Okay, so let's do this example. High energy subatomic particles coming from space interacts with atoms in the Earth's upper atmosphere. And then this collision will produce particles called muons. And muons, right, we have created muons in the laboratory before. And muons is an unstable particle, so it cannot last very long. It can only last, wait, let me open. I forgot to put this in front. Yeah, so yeah, muons can only last 2.2 microseconds on average, right? So, but let's just take this time interval. So muons can only last for this long before it dies or decays. Then, but this muon, right, from the atmosphere is traveling 9.95 C relative to the Earth. So, how long, if you are measuring the moving muon, how long does it last? Okay, so if let's go to full screen again. So according to our muon results, if we are measured at rest, then the time interval that the muon can last is 2.2 microseconds. So microsecond means 10 to the minus 6 seconds. Measured at rest means, okay, the muon is there, measured with you. The muon is not moving relative to you, so it's being created. It lasted for 2.2 microseconds and then it dies. So the birth and death happen at the same place. So this is the proper time. Okay, so that is the proper time. And then so now the muon is now the moving muon in the atmosphere. The speed is 0.990 C, 990 or 995? 995. Okay. Wait, I think I should correct this. It should be 990. Okay, so let me say 990. Because 2.2. Okay, fine. Let's follow 995. Okay, so moving muon in the atmosphere is moving at this speed, right? Relative to Earth. So from this u, I can calculate my gamma. So my gamma is 1 minus u squared over c squared. So this thing divided by c squared is just going to be 1 minus 0.995 square, the square root, and then this number, it turns out to be 10.1025. So I got 10.0125 over here, right? So then the lifetime of muon, so lifetime of muon measured by Earth observer is dilated. So my lifetime is just gamma delta T0. Okay, so it's just going to be 10.0125 times 2.20 times 10 to the minus 6. So basically, if you calculate, it's just like almost times up like 10. So it's 2.20 times 10 to the minus 5 seconds. So this is 10 times longer than we expect. Okay, so this one is actually an experiment that people have actually done before, and this is another confirmation of special relativity. So right, time dilation, it really do happen for fast moving particles, because we know a muon lasts for how long, right? So muon lasts for 2.2 microseconds. We have done this. People are very familiar with this experiment in the lab. But then when they measure muons in the atmosphere, right? So like all the cosmic particles crash into the atmosphere of the Earth, and then they create all these particles coming down at very high speed. Then these particles coming down at very high speed, right? They seem to last 10 times longer than the laboratory muons. So, but yeah, so that means time for the muon has been dilated relative to the observers on the Earth, because muon is now moving relative to the Earth. Okay, so that is the example of 10.3.1. Okay, any question? what was the? Yeah, so easy way to remember is other people time moving relative to you is always slower, right? And the calculation is all in the train experiment. Almost, not really, yeah. So we will come to the twin paradox after this example. Okay, so after this example, 10.3.2. So now I have another particle, right? So another particle is called a kaon, I think. K positive is unstable also. It can decay. The lifetime for kaon is 0.1237, so it's shorter than a muon lifetime. So let me record this down. Okay, so if measured at rest, the lifetime that you measure if you're at rest is 0.1237 microseconds, so 10 to the minus 6 seconds. Okay, and then now you're moving. Now kaon is moving at the speed of 0.990 relative to observer. Okay, so relative to the observer, how far can it travel according to the laboratory? So this one is pretty straightforward. We just need to know the time. We already know the speed, so we just need to know the time to get the distance that it can cover, right? So using time dilation, right? So the time measured by the observer is gamma delta t0, right? So this is the proper time. Okay, so proper time, so it's just delta t0 over 1 minus u square over c square, the square root. So this is 0.1237 times 10 to the minus 6, and then u is 0.99, so it's 0.99 square, the square root. So the time taken, the time it lasts is 8.769 times 10 to the minus 7 seconds. Okay, so it lasts a bit longer. So during this time, okay, so during this time, the kaon can travel a distance L. Okay, so yeah, so L, right? Just call this L. And because I know the speed and I know the time, so the speed is u. So u is supposed to be L over delta t, so L is u delta t. So it's going to be the u was 0.99, so speed of light, so 3 times 10 to the power of 8, and then the time interval is 8.769 times 10 to the minus 7. So from here we can calculate is 260.4 meters. So the distance traveled is given by this. Okay, so this the kaon can travel this distance if, because it lasted much longer than normal, right? So if the time interval is shorter, then the distance it can travel is shorter. So you can actually measure the time interval by knowing the speed and the distance. Okay, so it's the kinematics. Yes, correct. Basically, yes, time is slower because it's moving faster. Time is slower compared to other observers. That is the thing, right? From your own perspective, everything happens per normal. So this is, we're talking about the postulate one. Everything happens in the same for all inertial frames. So like the movie Interstellar lah, right? I know not everyone saw the movie before, but there's a scene where, you know, the two people on the spaceship, well, there's a group of people on the spaceship, and then a few of them travel to a planet where there's time dilation. Okay, so then they land on the planet, then they got some action sequence, so everything happens as per normal. But then when you come back already, right, the partner that they left behind on the spaceship become an old man. So the time has run differently for different persons. So that is the reason. That is partially related to the twin paradox. But the time dilation for the interstellar is due to gravity. That is a general relativity effect. Yeah. Any other question? Yeah. Let's not talk about interstellar because that's in general relativity. So let's not touch that yet. We haven't fully understand special relativity yet. Okay. So let me bring up the twin paradox. And then you can think about it during the break. Okay. So yeah, so for the twin paradox, right? So let's say I have so twin paradox. Okay, so twin paradox is, let's say I have two identical twins. I'm going to call this Woody and Buzz. Okay. The idea of using identical twin is, by right, normally identical twins, they are the same age, right? All the time, they are born together. So identical twins, we call them Woody and Buzz. But Buzz is an astronaut, so Buzz travels on a spaceship. On a high velocity spaceship. Okay, and then Woody stays on Earth. Okay, so because Buzz have a high speed spaceship, there's going to be time dilation. Okay, so there's going to be time dilation, and then so when they come back to Earth, right? So when Buzz returns, who will be older? And who is younger? Brightness. Okay, so when Buzz returns, who is older, who is younger? Okay, I think a lot of you know the answer to be Buzz younger. That happened in the movie Interstellar, and yeah, it happens in all the other solutions. But why? Okay, but where is the paradox? Because right, let's measure the age. Okay, so how do we measure the age? So let us measure the let both friends measure heart rate. So okay, so delta t, right? So according to so Woody stays on the spaceship, right? And then Buzz travels on the Woody stays on the Earth, Buzz travel on the spaceship. So according to Buzz, Woody is moving away. Moving away. Okay, so Woody heart rate is the proper time. Is proper time for Woody. So from Buzz perspective, right? Buzz measures Woody's heart rate to be delta t measured by, so Woody's heart rate is going to be gamma delta t Woody, but the Woody's proper time is 0. So from Buzz perspective, Woody's heart rate is experiencing time dilation, but according to Woody, Buzz is moving. Okay, so then Buzz heart rate is proper time for Buzz himself. So Woody measures Buzz heart rate to be delta t of Buzz to be gamma delta t bus 0. Okay, so what does this say? So bus say Woody is younger. But Woody say bus is younger. So that is the paradox, right? So yeah, was it Kai Shen? Yeah, or Kai Heng said that, I forgot who, sorry. I'll talk about this before I open the chat again. So, yes, the key to twin paradox is the proper time, and the key to calculating time dilation is always the proper time. But if you're talking about who is growing older, right, then the growing older is a biological process. So I say the heart because heart is a periodic time interval, so I can get a delta t there. Okay, so that is fine, right? So so according to this reasoning, right, both of them say the other person is younger. Okay, but they cannot be true, right? Eventually bus will return to Earth, and then when they stand side by side, then you can definitely answer the question who is definitely younger. And if you again, right, if you see the movie Interstellar, or some of you have already get the solution, is that the correct answer, we know the correct answer, right, is the answer is bus is younger. So what is the mistake in this calculation here? Okay, like I said, right, the answer is actually very boring, but I'll let you guys think about it, because the answer is boring, but the thought process is kind of help us practice understanding special relativity. So I guess now is a good time to take a break, right? Keep moving to be younger. Yeah, so yeah, let's take a break, and we'll come back again in 10 minutes. I will tell you the solution to the paradox. So 10 minutes break and top speed. Keep moving in light speed. I mean, yeah, 10 minutes break. So I'll stop the recording. So we come back on 11:07. Twin paradox. Okay. So yeah, so the idea is now I shall start drawing the picture. Right. So what is happening here is that Woody is on Earth, right? So Woody, okay, Toy Story Woody, he wears a hat. Okay, and then Buzz is on a spaceship. So how to draw a spaceship? Okay, so Buzz is here, and then he have to turn back and come back to Earth. Okay, so having to turn back and come back to Earth, right? Yes, so that is the explanation. That's a better way to say, yeah. Clock measure its own time in its own frame. Yeah, so if you take a clock and then clock will obviously clock will serve as its own frame. You measure its own time. So that is how we know that the time in this frame runs slower compared to another frame, right? So but for this, right, so the solution for twin paradox is this. Okay, so the answer is what actually happens is Buzz is younger. Okay, and because the reason is because, right, well, at first, okay, Buzz is traveling at this velocity u, so my velocity v as a vector is let's say u in the I direction, and then when it comes back, then the speed of the velocity of Buzz is traveling in the opposite direction. So Buzz has changed velocity. Okay, so Buzz has changed velocity. So Buzz has changed velocity. That means an acceleration has occurred. So that means Buzz is not an inertial frame. So if Buzz is not an inertial frame, then if one of them is not an inertial frame, then the special relativity calculation is cannot be applied anymore. That means you can say one of them is correct and one of them is wrong. Before that, right, if all of them are inertial frames, we cannot say who is right, who is wrong, right? Because everyone get their own measurement is perfectly fair. But here, right, bus is experiencing an acceleration. So when bus is experiencing acceleration, it's no longer inertial frame, so we cannot actually use the time dilation formula. So then this formula actually is not valid because it's not an inertial frame. That's why the answer is very boring. The boring answer is this calculation cannot be applied. Yeah. So the way to apply is for accelerating frames, and for that we need to use the methods of special relativity, which which is a bit more difficult, so we shouldn't do it here. So that's the boring answer, I guess. So Woody is on the inertial frame. Yeah, so Woody is not accelerating. Woody is just staying there. Even if the Earth is moving, we assume it's moving constant speed. So Woody is an inertial frame. Yeah, so it is an inertial frame. Okay. So what you can do, right, is like, okay, you can say that during the time where bus is moving at constant speed, you can use the time dilation calculation. But to say who is younger, right, what you need to come back to compare. So the minute you come back to compare side by side, then you need to do an acceleration, and then it's no longer inertial frame anymore. Then you can determine who becomes younger in that sense. Okay, so yeah, the answer is not very satisfying, at least to me, you know. Yeah, next sem, I think next year. So modern physics is mostly quantum mechanics, so we haven't learned general relativity yet in your next sem. Yes, correct. So the important thing is the inertial frames, and if you want to do comparison, then you need to make sure to, so comparison, you need to put everything back into the same frame, right? So to put back into the same frame, you need to do an acceleration. Okay. If the two frames are moving, then it's no acceleration, but you need to, so like Alice and Bob are moving, right? But if you want to compare, Bob needs to come back next to Alice, so that's an acceleration there. Then you know which one is the longer time, which one is the shorter time as well. Okay. Yeah. Any other question? So time runs slower. So back to inertial frames, right? If everything is inertial frame, then if you look at other people's frame, it is going to run slower. Okay. So if you look at other people's frame, then other people's time is not your proper time, right? If you look at a clock, someone wearing a watch, right, and then you look at someone's watch in a moving frame, that watch is not measuring your proper time. It's measuring the person's own proper time. So the time in another frame is moving slower. So you can imagine, right, if you look at something, if you watch a movie in another moving frame, the movie is actually running slower. And if you look at a person walking or running in a moving spaceship, right, then you can imagine the person running in slow motion compared to you, because time runs slower in another frame. So if you look at things happening, right, in a different frame, then things are moving slowly from your perspective. So that is the strange thing over there. Okay, so yeah, 10.3.2. So that is any other question for time dilation? Correct. The twin paradox, yeah, because accelerating frames, we have not learned how to solve accelerating frames yet, which is why I say the answer to this paradox is boring, because or not satisfying, because we can't solve it yet. If Woody and Bond on the spaceship drop on Earth and keep sailing, so Buzz will get older. No, it's still the same thing, right? So Woody drop on Earth. So Woody now becomes an inertial frame. Buzz continues sailing. Then, but if they want to come back together and meet each other again, you still need an acceleration. So Buzz will get younger. Woody gets older. So Interstellar, right? The Interstellar movie is the main character, Matthew McConaughey. He has a daughter. The daughter left behind on Earth. Then the Matthew McConaughey fly on the spaceship, right? And then when he come back, the daughter become like a old grandmother already. The father is still like 30 years old, 40 years old. Yeah. Doing slow motion means yes, that's true. The speed of the spaceship is high speed, but everything that happens inside that spaceship is slow motion from your observation. But if you're on the spaceship itself, right, you are doing everything as per normal, you don't notice it. If you're on the spaceship, you're looking away at the Earth at constant speed, then things on Earth is at slow motion. So that is where it happens. Yes, inertial frame. So inertial frame, not to say relative to universe background, but relative to each other. So if you talk about Buzz and Woody, right, Buzz and Woody, there's going to be acceleration relative to each other. So we don't need to say universe got background, right? So as long as relative to each other, because when you talk about relativity, we have frame S observation and frame S prime observation. Okay, so that's the only two important thing that matters over here. So only relative to each other. No need to care about universe background, because yeah, that's the idea of special relativity. There's no absolute correct background. Right? Okay, so yeah, so just relative to each other, no absolute background. Okay. Yes. Yeah, so every observer is stopped at its place, but also every observer, that is where we go into general relativity already, right? So inertial frame here means another important thing is there is no gravity. Okay, so if you include gravity, right, then gravity can distinguish between accelerating frame and not accelerating frame. So that is the another issue there. So which we again is in general relativity. So we can't really talk about this. So for our purposes, right, inertial frame means every frame is moving at constant speed relative to each other. Yeah. So this one is so these are the issues relating to accelerating frames, which is we need the general relativity to solve this. Yeah. So it's more tricky than that lah. So for special relativity, everybody is moving at constant speed relative to each other. So we just consider the case where Alice and Bob are moving at constant speed relative to each other. So this is the key point here. As Bob is moving at constant speed relative to Alice. So we are only capable of calculating this situation for now. Yeah. Two frames, constant speed relative to each other. And we'll see why lah. I think by Monday we will do this. Okay, so yeah, so we have seen how time works differently across different frames. Now we calculate distances now, and distances also works differently across different frames. So we will see how it works like this. Yes, yeah. So work is the one that we know that can tell us who is accelerating, and yes, that is true. So this is the reason why Buzz has not an inertial frame. Yes, and then Woody is just sitting on the chair doing nothing. So Woody is the inertial frame. Yeah, that is one way to identify. Yeah, so that's one way to identify. So that's okay. Okay, so so for next thing is we now consider length measurements, right? So we come up with another thought experiment. Instead of measuring a time interval for a laser, we now measure the distance traveled by a laser. Okay, so and using this distance, we measure a certain rod. So let's say, right, Alice and Bob measures the length of a rod, or let's call this a ruler, using light, laser. Okay, so the ruler is on the train together with Bob. Okay, so yeah, so then okay, so let us consider this scenario. If a giant volcano explodes and Earth is moving, is still inertial frame. Well, then then Earth is the one that is accelerating now, and then yes, and then the Buzz is having the inertial frame if Buzz is not doing anything. Yeah. So like the movie, right, the Wandering Earth, the Wandering Earth thing. So the Earth itself become the spaceship. Okay, so for length measurements, let's see what happens in Bob's frame. So both of them attempts to measure a ruler. So let me draw the situation here, right? So what is happening here is, okay, so Bob is on a train. Okay, so Bob is on a train, and now I shine a laser in this direction. So laser is here, and then the length of the rod is, this is my rod. Okay, and then there's a mirror. Okay, so the rod is here, and then Bob is on the train doing this experiment. Okay, so the laser will shine, and then it will travel across the rod and then hit the mirror and come back to the starting point of the laser. So from the perspective of Bob, right, nothing is moving because everything is in a train together. Okay, so the rod is here. Okay, so the mirror is here, and then the laser will just shine onto the mirror, and then it will get reflected back. Okay, so that for Bob's case is everything is very simple. So what does Bob measures? So Bob measures distance traveled by light is equals to 2L0. So let's say length measured, length of ruler according to Bob is equals to L0. So the distance traveled by light is 2L0. Okay, then the time interval is some delta t, right? So delta t is the proper time for Bob. Okay, so time interval during this process is delta t0. Okay, so this is the proper time, right? Why? Because the light leaving and coming back is still in the same location in the Bob coordinate system. So this is the proper time. Okay, so then speed of light measured by Bob is going to be c is equal to the distance traveled by the laser, and then divided by the time taken for this process. So that means the time interval for Bob is delta t0 is just 2L over C. Okay, so this is Bob's measurement. Okay, so this is the time interval for the Bob. Hopefully everyone understand this at least so far, because the Alice measurement is going to be a bit more complicated. So let me try my best to draw it nicely. Proper time is the train's frame, correct? Yes. Yeah, so as the main point is living longer means you need to actually, right, what Hawking said is not actually correct, because if you are moving, even if you are moving relative to other people, right, and even if your time is slow as observed by other people, but you observe your own time behaving normally, you observe your own proper time. So if you live 100 years on a moving spaceship, you still die at 100 years old, right? Even though for relative to Earth, you live more than 100 years because of time dilation, but your own experiences is you are experiencing 100 years only. So you do not actually live longer, but what you can say is you can travel to the future faster than other people if you are on a moving spaceship. You know what I mean, right? About the time dilation. Okay, so if not, never mind. Let's not confuse about this yet, because right now we have this thing to worry about. Okay, so let's see what happens in Alice frame. Okay, so Alice is observing a laser on a moving train. So this is a bit tricky. Okay, so let me draw this situation step by step. So I draw step 1. Step 1 is the initial time. So initial time is my starting point where the laser is starting. Okay, so my rod is here. Okay, so let's say our length of ruler measured by Alice. I will call this L, right? By Bob is L0. This is the mirror, this is the laser, and then Alice is standing initially next to the train, right? But the train is going to move in front of Alice. So this is step 1. So this is what happens at time 0. And then let's see what happens at step 2. Because the train is moving, so this is why it's tricky to draw. Let me try to draw this. The train is moving. So at some time later, right, the train is moving in front of Alice. So Alice will see the train move. So the train will be here now. Okay, so the train is moving relative to Alice. So this is my rod now. And then my mirror is here. Okay, so let's say, right, this is the time where the laser hits the mirror. So at time equals to delta t1, laser hits the mirror. Okay, so during this time, right, how far has the train moved according to Alice? Because the relative velocity is u, right? So the distance traveled sideways is u times delta t1. Agree? Okay, so this is what happens, right? So yeah, so then in fact, from Alice coordinate system, right, I draw wrong already. The light started from here, right? So the light started from here, and then the train is moving. So the light needs to travel until here to reach the mirror at this time. Correct? So this is the distance traveled by the light. Okay. So then the step 3 is the light coming back towards the laser. So let's go to step 3. Okay, so step 3, now the train is no longer here. Right, the train is no longer here, but the train continues to move forward in front of Alice. Right, so the whole time the train is moving in front of Alice. So my rod is now here. My mirror is here, right? So and then the laser is here, so it will come towards the laser here. Okay, so the distance traveled here now is equals to u times this time is time at delta t1. So this is another time interval, delta t2. So this is delta t2. Okay, so yeah, do you agree with this situation so far? Right, the laser travel and then it will hit the laser pointer again. So it will shine back on the laser pointer source again. So let's do our calculation now. Let's see what happens at step 2. So at step 2, right, at step 2, what is the distance traveled by the light? Okay, so now the length of the ruler according to Alice is, I call this L, right? So the distance traveled by the light is equals to L plus u dt, right? And then so therefore the speed of light is supposed to be c for no matter what frame you are using, but the speed of light is just the distance traveled divided by the time taken during this process, so delta t1. Okay, so I will rearrange this expression. So I've got c dt1 is equal to L plus u dt1. So I can solve this for dt1. I bring this over. This is L c minus u. Okay, so this is the time interval for step 2. So I calculated this time interval 1. I can now consider step 3 now to get the other time interval. So at step 3, okay, so yeah, just to clarify, laser returns to laser pointer. Okay, so at step 3, the distance traveled by the light is what? Well, actually, yeah, I think I draw the wrong picture. Yeah, so hang on. This is where you have to be careful. So I draw the wrong picture already. So let me draw this picture again very carefully. The distance traveled by light is not L. It looks like L, so I got the wrong impression there. So let me draw the picture again. The distance traveled by light. Because when it left the mirror, right? When it left the mirror was here. Right? So the mirror was here, but now the ruler, the whole system has moved forward. Okay? So the distance traveled by light is actually like this. Okay? So let me draw this one more time just to synchronize with this image. Okay? So my train is here. When it hit the mirror, right, the mirror was here. So the mirror was, this is the previous position of the mirror. Okay, then during this time interval, the whole system has moved forward. So now my mirror was here. So now my mirror is now here. So the distance traveled by the light is like this. Okay, so the distance traveled by the light is shorter, right? So the distance traveled by light is actually L minus u delta t2. Okay, so from here we can get the speed of light again. So u delta t2 divided by the time interval. So I can solve this for delta t2. So delta t2 is L minus u dt2. So dt2 is L over c plus u. Okay, so I got these two expressions over here. Okay, yeah, I'm sorry for the confusion. So does anyone have any question? Is this clear? This is the correct one, this is the wrong one. So this picture is wrong. I draw it wrongly. Okay. One day in heaven, one day earth. Only time is different frame, but same for the observer. Oh, yeah, kind of makes sense, I think. In the picture of step 3, what changed? So this is where I what do you mean what changed? You mean what was my mistake? Yeah, so in this picture is wrong. Yeah, so that's the distance traveled is wrong. So the distance traveled in this mirror is shorter. Because the light is leaving the mirror after step 2, and as the light travels away from the mirror, the train also travels forward. So the train is going into the light, and so the distance covered by light is shorter in step 3. Okay. Yeah, so I let you digest this picture while I clear my nose. My nose got problem again. Okay, does it make sense? This picture. Your stomach explode. Oh, you mean your brain, right? Because this one is our brain is doing the digesting. Initial and final position of the mirror. I think can also. But we need to get the delta t. I just want to get the delta t1 and delta t2. Yeah, I just want to get these two expressions. Yeah, for step 1 and step 2. Because the total time interval, the reason is because the total time interval is going to be the sum of these two. 3, 4, 5, 6. Okay, so total time interval according to Alice. Okay, so total time interval according to Alice, measured by Alice, is delta t is dt1 plus dt2. Okay, so L is c minus u. So dt1 is what we got just now, and dt2 is c plus u. Okay, so let me now simplify these two expressions. So the two denominators, if I multiply them each other, I'll just get c squared minus u squared. And then this is L c plus u. That's another L c minus u. So plus c minus u over here. Okay, so I can cancel the u. So this is 2lc over c squared minus u squared. So this is delta t. So the time measurement according to Alice is 2lc over c squared minus u squared. Okay, so now I got the two time interval measured by Alice, right? And then measured by Bob was, we got this earlier. Time interval for Bob was this. Okay, so we now have the time intervals of the same event. Time interval between the same event measured by Alice and Bob. Okay, so Alice measures this. This is the same event. What is the event? The event is laser come out, and what is the time taken for the laser come out and come back again? So how long does it take, right? So according to Alice, she got this result, and according to Bob, Bob got this result. So 2L over C. Okay, so who gets the proper time here? Bob, right? Because the laser is together on the Bob's train. So the laser is on the fixed position on the Bob's train. So it come out and come back on the same position. So therefore, Bob has the same, so Bob gets the proper time. we now use the time dilation formula. So I know who is the proper time, and this is not the proper time. Why Alice is not getting the proper time is because in the Alice coordinate system, right? So I draw the X position here for Alice, right? The laser is starting here, but it comes back at some position on the right. So it's not the proper time. So these two events is not on the same position in the Alice coordinate system. So therefore I can use the time dilation formula. So the time dilation formula is, this is the correct formula to use, right? So on the left hand side I substitute 2LC over C squared minus U squared. Gamma is 1 over U squared over C squared, square root, and then the Bob time is 2L over C. Yeah, 2L over C, I think it's correct. So I cancel the 2 on both sides. I bring the C here, so I got LC squared, C squared minus U squared is equals to Bob L, right? And then I will simplify because I can factorize this out. Oh, I forgot to copy this down. Okay, so this is basically L 1 minus U squared over C squared, the square root, right? So I cancel this. Then this one is the square of this, right? So if I bring this up, I got L is equals to L0 square root of 1 minus U squared over C squared. And what was this? This was 1 over gamma. Remember, this is the Lorentz factor is 1 over gamma. So I conclude that this is L0 over gamma, where gamma is my Lorentz factor. So the length measured by Alice is, gamma is a, remember, right, gamma is always greater than 1. So I'm dividing by a number that is greater than 1. So if Bob measures some length, the Alice result will be shorter. So this is length contraction. Okay. I think it will be the same. I have not tried. I have not tried the calculation. Yeah, I think it should be the same. Yeah. Okay, so both are observing the same speed of light. Yeah. So both measure the same speed of light. Therefore, the Alice distance and time will be different from Bob distance and time. Correct, correct. Bob's time and Bob's distance. Yeah. So, correct, yes. Yeah, I think you got it. Yes, exactly. The key point is we can only trust that both measure the same speed of light in both frames. But the time interval, right? So the time for Bob and Alice is different. The length measured by Bob and Alice is also different. And we just use the fact that these two are equal. And then also we use our, this formula also came from this equal, right? So we calculate everything and then we can get a relationship between the two. Okay, so as the lesson that we learn is Alice and Bob, they measure the same speed, right? But the length they measure is different. The times they measure are also different. Actually, time dilation formula is here. Yeah, so time measured by Alice is different, time measured by Bob is also different. Okay, so yeah, so I guess good. Hopefully everyone is also on track in understanding this. Yeah, so if we overcome our initial confusion, right, actually it's very simple. The simple thing is, in fact, it's even simpler than Newtonian mechanics because we just need this constant. Speed of light is always a constant. And then we use this constant to calculate everything else. So it only relies on one thing. So that is the simple, the simplicity of the special relativity. Okay, so now the lesson that we learned is not just time is different if you observe other people's frame, the lengths also appear different, right? So if we observe the length, the ruler will appear shorter if seen by Alice. So that is what is happening here, the length contraction. Okay, so now similar to proper time, right? This arises another question as well. So let me ask you another question. Okay, so what was the two names that I was using? Eve and Carl, right? So if Eve and Carl, or Woody and Buzz, right, measures length of Eve and the length measured by Carl. Okay, so and Eve and Carl are moving relative to each other. So which one should we use? The length measured by Eve is Carl divided by gamma, or the length measured by Carl is Eve divided by gamma. So the solution is, to avoid making this mistake, we must identify the proper length. Okay, so the answer is length measured is equals to proper length divided by gamma. So we need to identify who has the proper length. Okay, so we need to identify who has the proper length. So let me now define what is the proper length. Okay, so the proper length proper length is the length measured by the frame where the object is at rest. Okay, so in our thought experiment, right, okay, who has the proper length, right? The ruler, where is the ruler? The ruler is on the train together with Bob, right? Alice is outside seeing everything moving, so Bob has a proper length. So ruler is at rest with Bob. So length measured by Bob is the one that is the proper length. Okay, then also clearly the ruler is moving relative to Alice. So Alice is not proper length. So from here, the Alice measurement is the one that is proper length Bob divided by gamma. So this is how we identify who has the proper length. Okay, so Bob has the proper length. Clear? Okay. What time is it now? So I think yeah. So that's the lesson postulate 2. We always observe light as 3 times 10 to the power 8 meters per second, no matter what frame we are using. Yeah. So let's go to let's finish this example before we end the class. This is a very short example, 10.3.3. Okay, so let's so this picture is a better description. So if my drawing was very messy just now, so better look at this picture to help us understand. Okay, a spaceship flies past the Earth at 0.99 CE. A crew member measures the length of the ship to be 400. What is the length of the spaceship if you observe it from the Earth? So let us perform this calculation. Okay, so so crew on the spaceship measures 400 meters, so the proper length is 400 meters. Okay, and then shape is moving at 0.99 c relative to Earth. Therefore, Earth observe the length to be length contracted. So the length measured by Earth is going to be contracted by gamma, right? So 1 over gamma is just the square root upstairs. So I got L 1 minus u squared over c squared, right? So my L was 400 meters, and then times 1 minus 0.990 c square root. So if we calculate the number, you are going to get 56.4 meters. So a moving spaceship also appears shorter if it's moving relative to you. So that is another strange phenomena coming from special relativity. Okay? Yeah. So does anyone have any other question? So a lot of strange things, we have been discussing a lot of strange things, right? Time is weird. Time works differently for different people. Space works differently for different people. And definitely, it needs time to digest. Real life edition for Stranger Things. Yeah, I guess so. Stranger Things is not that strange, right? We don't have time dilation in Stranger Things. They have the upside down, but time works the same way in upside down as well too, right? Okay, so if there's no other question, well, you can ask your question here, but that's all I have for today's class, so I shall stop the recording.